All right, let's dive right into this explainer. Today, we're talking about the literal foundation beneath our feet by examining the classification and formation of rocks. We interact with the Earth every single day, but we rarely stop to actually consider the incredible, massive geological forces that built the very ground we stand on.
We've got a fantastic roadmap for today. We're going to start with the basic building blocks of Earth, then move right into igneous rocks with their molten origins, explore the rebuilt fragments that make up sedimentary rocks, and finally wrap up with the extreme alteration of metamorphic rocks. Okay, Section 1, the building blocks of Earth. What exactly is the crust made of? To begin, we have to ask, what is a rock, really? Basically, it's defined as a hard mass comprising two or more rock-forming minerals, and it's the direct outcome of absolutely powerful geological forces. Now, when we look at the entire Earth's crust as a whole, there's an overwhelming dominance of igneous rocks. They make up a staggering 95% of it. That leaves just 5% for sedimentary rocks. It is a massive, molten-derived foundation. But here's where it gets really fascinating. If we zoom in and just consider the upper 5 kilometers of the Earth's crust, the part we actually live on and interact with, that composition brilliantly shifts. Suddenly, sedimentary rocks totally dominate at 74%. Igneous rocks drop all the way down to just 18%, with other rocks rounding out the final 8%. It's an absolutely crucial framing for understanding the surface of our planet. Moving on to Section 2, igneous rocks. Let's explore their molten origins and how they act as the parent material for all other rocks.
You can think of these igneous rocks as primary rocks. They're formed by the cooling and consolidation of magma. And magma is just this incredibly intense, complex, hot solution of silicates mixed with water vapor and gases. It originates way deep down in the Earth's crust, and it reaches mind-boggling temperatures. We're talking anywhere from 700 to 1400 degrees Celsius.
Now, depending on exactly where that 1400-degree magma decides to cool down, we get a really interesting split. On one side, we have volcanic rocks. These actually form on the surface of the Earth. And because they cool down really quickly, they form fine-sized crystals and end up with this glassy structure. Think of rocks like basalt. We call these extrusive rocks. But on the other side, we have plutonic rocks. These form deep within the Earth's crust. Because they're insulated down there, the cooling process is super slow, so crystallization takes a long time. This results in coarse crystals you can actually see with the naked eye, giving them a really hard, massive structure. Granite is a perfect example of these intrusive rocks.
Beyond just where they cool, we can also categorize these igneous rocks by their chemical makeup, specifically their relative amounts of acid and basic components. Now, the acid component here is silica. It's basically a step-down process. We start with acid rocks, like granite, which have over 65% silica. Then we step down through subacid, subbasic, and basic rocks, all the way to ultrabasic rocks, which contain less than 45% silica. Okay, here's a perfectly surprising example of an igneous rock for you. Pumice. It's a light-colored, extrusive rock that's formed by the escaping of volatile constituents. Basically, as the lava frothed up to many times its original volume because of expanding gases, it created this cellular structure that looks almost exactly like a sponge. And because of that trapped air, it actually has a lower specific weight than water. Yeah, it literally floats. It's such an amazing illustration of how trapped gases can completely change a rock's physical properties. Let's transition to Section 3, sedimentary rocks. This is where we see how those pre-existing parent rocks break down and become rebuilt fragments to form stratified secondary rocks. So how exactly does this rebuilding happen? Well, it follows a highly ordered 4-stage process. Stage 1 is weathering, where primary rocks literally disintegrate thanks to physical, chemical, and biological factors. Stage 2 is transportation, where things like water, wind, glaciers, or even just gravity move that fragmentary material around. Stage 3 is deposition, where all that material finally settles. And the 4th stage is digenesis. This is where unconsolidated sediments transform into hard rock through 2 sub-processes. First, compaction, where the sheer weight of thousands of meters of upper layers just squeezes out the water and air. And second, cementation, where percolating water deposits binding minerals, like lime, silica, or iron oxide, right into the remaining voids. During that 3rd stage deposition, we actually see a really logical phenomenon called graded bedding. Simply put, when whatever is carrying the material, say water, loses the energy needed to keep moving those detrital pieces, the heavier, coarser particles drop out and settle first. The finer, lighter particles settle later.
This creates a perfectly graded layer of sediment.
Once all those fragments lock together, we classify them based on their exact origins. For instance, if the weather products just settle right exactly where they formed, we get residual rocks, like bauxite. If the transported and cemented fragments form beds of varying thickness, we get mechanical rocks like sandstone. We also have chemically formed rocks, which are created either through evaporation, like halite, or precipitation, like limestone. And incredibly, we even have organic or biochemically formed rocks. When plants decompose under a restricted air supply in the lower layers of the Earth, a massive chunk of their carbon is retained, and over time, that slowly converts into peat or even hard coal.
And that brings us to Section 4, Metamorphic Rocks. The key theme here is extreme alteration, a complete change in form. This metamorphosis happens when deeply buried igneous or sedimentary rocks succumb to intensely extreme conditions. These complete changes in form are driven by the combined action of three massive catalysts: chemically active fluids, internal heat, and extreme pressure. This brutal combination completely alters both their physical structure and their mineralogical composition. It often results in this banded or laminated look that is pretty much the defining, peculiar feature of metamorphic rocks. Think about the extreme before and after of these catalysts. It's fascinating. Under massive pressure and heat, a primary rock like granite will partially foliate and turn into granite gneiss. A relatively soft sedimentary rock like shale gets compressed into slate. Intense heat can literally bake limestone into crystalline marble. And that organic coal we talked about earlier, under these extreme conditions, it transforms entirely into graphite. It just goes to show you how dynamic the Earth's crust truly is. Based on their final texture and the way their minerals are structured, these altered rocks are divided into three distinct groups. First, we have foliated rocks. These contain micas and ferromagnesium minerals that get flattened and arranged into parallel layers. Think schist or slate. Second are unfoliated rocks. These contain quartz and feldspars and maintain a massive structure, simply because their large-sized crystals resist showing that foliation, even under intense pressure. And finally, we have granular rocks, which consist mostly of equidimensional grains, like quartzite or marble. As we wrap up this explainer today, there is one absolutely vital takeaway you need to remember about all these rocks, and it's their weatherability. Whether an igneous, sedimentary, or metamorphic rock breaks down quickly or slowly is dictated entirely by its specific mineral makeup. The rule of thumb is quite simple. Rocks made up of ferromagnesian minerals, like olivines and pyroxenes, are more weatherable. That means they're going to break down way faster than rocks made up of non-ferromagnesian minerals. So the next time you walk outside, think about that 74% of the upper crust that is sedimentary, or the 95% of the total crust that is igneous. And ask yourself this: is the literal ground beneath your feet made up of highly weatherable ferromagnesian minerals? And if it is, how soon will those very rocks begin their cycle of breaking down, transporting, and rebuilding all over again? Thanks for joining me on this deep dive into the incredible foundation of our Earth.